that week 12. Okay, so so this week we are mostly looking at uh, rank approximation, low rank approximations. So write it down. Uh, as per the usual style, I'll try to cover some theory, and then we'll look at the problem solution.
That will be
So
good. Mhm.
yeah, yeah, sure. So let's look at the main topic for this week, which is mostly around low rank approximations. Right. So in low rank approximations, we are given some data matrix, and what we want is the data matrix can have a huge size, uh, but we do not necessarily want to deal with uh, such a huge size. Okay. Uh, an example would be, let's say, uh, in operator theory. This is not really from data analysis side, but more from like function analysis side. So in operator theory, it is common to encounter uh, uh, operators which have a large rank. Okay, and we may want to approximate those operators by some operator which has a lower rank. And there are many advantages to this, to doing this. In particular, in analysis, uh, there are uh, there are many applications where these low rank approximations are useful. In data analysis, when it comes to data analysis, it is mostly one common application is in what I would say as compressions. So we're given some form of a data matrix, and we want to compress the data matrix. So so the rank of the data matrix captures, in some sense, the number of distinct features that are there that data matrix. And so we may want to preserve a certain number of features, and we may not want to do it. So our idea is to save space, time, etc., which is why we want a low rank approximation. Uh, in particular, so let's say A is some matrix, uh, or in Rm cross n, and we want some, let's say, rank of A is equal to some k, and we want or let's say the rank of A is equal to R, and we want a matrix A tilde such that uh, the rank of A tilde is at most k, where k is generally taken to be smaller than R. And of course, there can be many such A tildes, but we want an A tilde which is closest to A. So we want something that closely approximates A as closely as possible, but has a low rank. So, uh, and when it comes to approximation, we're looking at distances. So we want this to be minimized. We want to minimize this subject to the criterion that rank of A tilde should be at most k. Okay. Now, of course, such a minimization program would depend upon the choice of the norm. Okay, and based on the choice of the norm, uh, the minimum A tilde would vary. Now, of course, one may ask, what is the appropriate norm? The answer is there is no appropriate norm. The appropriate norm uh, generally depends upon the application that we are dealing with. There are two most commonly used norms. One is the operator 2 norm, and the other is the Frobenius norm. There are advantages and disadvantages to both. Uh, the the uh, the 2 norm has obviously has certain advantages, but when we want to have an optimization program that minimizes for this 2 norm, the so we know that the 2 norm is minimized. We basically know that if given a matrix, then the 2 norm would basically be equal to its largest singular value, right? Now, uh, if we want to solve this minimization program, then we have to basically ensure that the largest singular value of the difference, that is a minus a tilde, that the largest singular value has to be minimized. In other words, um, in other words, the we need a function that uh, uh, that so basically for a minus a tilde, there is some function rho of a tilde, uh, or let's say a maps to rho of tilde, which is that. Okay, let's just say a minus a tilde. So there is a map which takes it to the largest singular value of a minus a tilde. I mean, this is not the standard notation. The standard notation is actually this. Uh, so the so we want to basically minimize this. Now, this sigma is not really an analytic function. It's a function, but it's not a function which is always very conducive to doing some kind of analytic minimization program. The Frobenius norm has more advantages because the Frobenius norm, you can write the Frobenius norm as a sum of squares of the elements of a and a tilde. So as long as we can represent this a tilde as some matrix where the entries are unknown, uh, all you have to do in theory is uh, is solve for the minimization of these quantities. But there are other possibilities also. I mean, by that I mean there are uh, uh, other constraints that may be included. We will discuss about that moving forward. So in general, both these norms are useful when it comes to these low rank approximations. Now, we'll look at a particular case, which is a kind of unconstrained low rank approximation. One can think about it in this way. So let me write down the first and uh, uh, the most fundamental case. So here we have a matrix A, and we want to uh, uh, compute a rank A uh, approximation of A. Um, so the approximator, if we call that as A tilde, then A tilde should have a rank exactly equal to K. And K of course is like a smaller rank than K. Now let's if we express this A as an SVD, uh, so so we can express this A as some uh, let's say, let us assume for now that A is some Rn cross n matrix. Then let us write this A as equal to sigma 1 U1 V1 transpose up to sigma n u un vn transpose. Then, so if you write A in this format, uh, we want to state a result. The result is as follows. Second. Yeah, this is called the Eckhart uh, Young Minsky theorem, which states that A tilde right, which states that let's actually put a subscript also. I want to use a subscript A tilde K, where K denotes the rank that we want to, the best rank K approximation. Then the best rank K approximation uh, is basically given by sigma 1 u1 v1 transpose up to sigma k uk vk transpose. In other, hopefully it should be clear that these sigma i's are arranged in a way that that sigma 1 is greater than or equal to sigma 2 and so on up to sigma n, right? So we look at the first k singular values and pick the right and left singular vectors corresponding to that. So this would be the best rank k approximation of A. We have not yet mentioned what norm we are using, and the Eckhart-Young-Minsky theorem basically states that for both the two norms and the Frobenius norm, this is the best rank K approximation. Okay, so you encounter a lot of problems of this kind where they may ask, uh, they may be asking to compute a low rank approximation of A, where a decomposition of A tilde K is given like this. And all we need to do is we need to pick the top K singular values and uh, and the corresponding singular vectors corresponding to them. Otherwise, in general, the standard practice would be to compute the singular value of A and get it from there. So this is a very important result to keep in mind. I'm not going to state the proof of this. The proof can be found in standard textbooks uh, or on the internet also. The Eckhart-Young-Minsky theorem proof can be found. Now, now the second uh, important uh, case is uh, a so-called constrained low rank approximation. Uh, Okay. So, so here we may be dealing with special kinds of matrices. Okay. So let's say again the input is a matrix A, but the matrix A is not just any matrix; it is a particular kind of matrix. So what are some commonly used kinds of matrices? So, for instance, A can be a symmetric matrix. Uh, it can be a skew symmetric matrix. Uh, it can be um, a upper triangular matrix, so on. A Toeplitz matrix.
Shall I
So
interfere?
yeah,
I,
please.
actually, what happened? My internet connection was gone when you discussed
Okay.
Eckhart-Young-Minsky theorem. Can you just
Yeah, yeah, sure.
say
I'm going to
it?
discuss it again. Yeah, 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 sure. I'm going to discuss it again. So the Eckhart-Young-Minsky theorem tells us that if you're given any matrix A and you want to compute a rank K approximation of A, let's denote that by A tilde subscript K. So this K is going to be the rank that we desire, and K is typically smaller than the rank of A. Okay. If K were equal to the rank of A, then simply A tilde would be equal to A, but K is smaller than the rank of A. And so the Eckhart-Minsky theorem tells us that if we write A in this way, so we compute the SBD of A, and then we write A as sigma 1 U1 V1 transpose up to sigma n UN Vn transpose. Let's say this is the SBD of A, where sigma 1, the singular values are arranged in descending order. So sigma 1 is greater than sigma 2, is greater than so on. Then the Eckhart-Minsky theorem tells that the best rank K approximation of A is given by just taking the first K singular vectors, uh, the first K singular values, sigma 1 to sigma K, and the corresponding singular vectors. So if there were n of, uh, if A has, so there are n minus K uh, extra terms that are there in the singular value decomposition of A, we simply drop those terms. We're going to just consider uh, the first K terms in the singular value decomposition of A. And this matrix A tilde K is going to be the best approximation of A, both with respect to the two norms and also with respect to the Frobenius norm. So this is what the Eckhart-Young tells us. So in a lot of applications, they may uh, they may uh, they may give a question of this kind where they require you to compute a low rank approximation of A. Sometimes they may say two norms, sometimes they may say uh, Frobenius norm. Uh, the optimizer, the yeah, the minimum distance matrix A tilde is the rank A will not change. Okay. So
Okay,
now we
okay,
come
that's
to
enough. Okay,
okay. So
okay,
now we
that's
come
enough.
okay. So now we come to constrained low rank approximations. So here the matrix A, uh, this is a variant of this rank K approximation, but there are further constraints imposed on the matrix A. So the matrix A can be of a particular kind. It could be symmetric, skew symmetric, upper triangular, it could be anything. In general, we are looking at a subspace of the space of matrices. So the space of matrices Rn cross M, this is a vector space. We are looking at some linear subspace, like basically a vector subspace of Rn cross M. So see, you notice that symmetric, skew symmetric, upper triangular, Toeplitz, these are all vector subspaces of Rn cross M. Uh, and okay, so let omega be a subspace, and we want to compute a low rank approximation a tilde k of A such that A tilde k also belongs to uh, sigma, and rank of A tilde k is equal to uh, k. Now, this is an example where uh, a strategy like this would not succeed because uh, uh, because if we pick the minimizer given by the Eckart-Young-Minsky uh, uh, Eckart-Young-Minsky theorem, then the minimizer need not belong to this subspace. So, for instance, let's say we are dealing with symmetric matrices, and what I want is a symmetric rank K approximation of A. This may not give me a symmetric rank K approximation, right? And yeah, maybe for symmetric it will give you uh, for a symmetric for symmetric this will actually give you the uh, rank cap optimizer, but in certain cases it may not be. For instance, let's say you're dealing with Toeplitz matrices, which is a particular kind of matrices. Uh, for a Toeplitz matrix, obviously. In general, the Eckart-Young-Minsky did not give a uh, did not give an uh, did not give an approximator, which is also going to be a Toeplitz. So here we may have to use some different strategies. Uh, Now this is of course a very large and extensive area of matrix analysis that is doing low rank approximations. We're going to look at one specific case, and I think that is what is there in this course, and see how to do this. So our case would be as follows. So the K, which is the rank that we desire. So K is equal to the rank of A minus 1. So we just want to drop by one rank. Furthermore, what we want is that we want to minimize with respect to the Frobenius norm. The reason why we choose the Frobenius norm is that the minimization program can be written down in an analytic form, which then allows us to use like standard methods in analysis to essentially it allows us to differentiate and set the expression to zero. Uh, that is the reason why we're going to minimize with respect to the Frobenius norm. And of course, the optimizer, that is sigma tilde k, also has to belong to uh, this this subspace omega. So to do this, first of all, we need to proceed as follows. Uh, the first requirement is that uh, we need to pick a matrix uh, from omega, right? So we have to let's compute a basis for omega. The first thing is compute a basis for omega. So an example would be as follows. So let's say omega is this is just an example. Omega is symmetric uh, 3 cross 3 matrices. Okay. So when we are dealing with symmetric 3 cross 3 matrices, uh, there are the diagonal entries. The entry here is equal to the entry here. Uh, the entry here is equal to the entry here. The entry here is equal to the entry here. So when it comes to choosing a basis, you can pick these elements, and these elements are then automatically determined. So a basis would look like this. A basis would have six elements in a basis, and uh, so not instead of writing the six matrices together, let me just write down in a more compact form. Uh, so the basis would be of the form Eij, where j is greater than or equal to 1, and uh, less than or equal to I, and of course I varies from 1 to n. N in this case is just equal to 3, and Eij is a matrix where so Eij is a matrix where the entries of the matrix is given as follows. So Eij, the p comma qth entry is given by this is just a fancy way of writing the canonical delta function I p times the canonical delta function j q, which basically means that Eij is a matrix in which the ijth entry is equal to 1 and all other entries. No, sorry, no, made a mistake. Yeah, so basically Eij is a matrix uh, where the I, okay, I should write it this way. Uh, hmm, JP IQ, right. So Eij is a matrix uh, uh, where Ij and Ji are set to 1 and everything else is set to 0. So in other words, it's a basis where let's say Ij is equal to 2 comma 1 or let's say uh, yeah let's say it is 2 comma 1. So then so E2 comma 1 looks like this. It has 1 over here, 1 over here, and the rest all the entries are set to 0. Okay. So this is just like a fancy way of writing that. Right. So there's going to be six elements in this basis, and likewise you have E21, you have E11, E22, E33, and so on. Okay. So this is an example of a choice of basis for omega. So the first thing is that the matrix that we're going to work with uh, is going to be a part of this basis, right? So so for a general case, so let y1 up to some number, uh, let's say yq, be a basis for omega. Uh, then uh, or not, let's not use y. Let's use e's actually. Let E1 to EQ be a basis of omega. And let me write any arbitrary matrix in omega. Uh, uh, we're going to write this y as equal to y1 E1 up to yq EQ. And let's say the matrix that is given to me, which is A, let's say A is again represented in this basis as some A1 E1 up to AQ, EQ. So we want to minimize. Yeah, so we want to minimize y minus a Frobenius norm squared, subject to the constraint that the rank of y is one less than the rank of a. Okay, assume for now that the rank of A is n. So A is a full rank matrix. So what we want in that case is we want yv to be equal to 0 for some vector v. Okay. Uh, for some v. Uh, Now we're going to represent this uh, just give me 1 second. Sorry, I need to state one thing. So we are not necessarily computing. So k is equal to rank k of a, rank k minus one. But the optimizer that we are computing, a tilde k is of rank less than or equal to k. That is, let me just write it down over here. Note that in this problem, what we want is that rank of a tilde k is less than the rank of A. Okay. Uh, we're not fixing the rank of A tilde K. We're just saying that the rank of A tilde K should be less than the rank of A. This is the setting of this problem. Okay. Of course, y of b is equal to 0 means that if A is full rank, then this means that the rank of y is one less than. It cannot be full rank. The y has a non-zero null space. So in this case, uh, when you're computing the Frobenius norm, uh, so the Frobenius norm is of course the sum of the squares of the entries of the matrix. So assume that uh, if we have any matrix, uh, let's say W in omega, which I write as equal to W1 E1 up to WQ EQ, then assume that if I express the Frobenius norm of W, then the Frobenius norm of W is equal to something like W1. Uh, uh, let's say, yeah, so let's say the Frobenius norm of W squared is equal to some W1 squared times some function of E1. So we're going to denote that function of E1 by, uh, let's give some name. Let's call it C of E1 up to WQ squared C of EQ. Okay. Suppose that for every matrix W, we can express the Frobenius norm in this way. So then, what we want to minimize is this. We want to minimize. Uh, we want to minimize sum over of yi minus ai CEI, where I is from 1 to q. We want to minimize the square of this quantity, and we want to minimize this over all yi's, subject to the criterion that there exists some v not equal to there exists some v not equal to 0, such that y times v is equal to 0. Okay, so this is what we want to, this is our minimization program. No, okay, so I said for all v, no. This is, there exists some v not equal to 0, such that yv is equal to 0. So now one may ask the question: what if y is, what if the matrix A, which is our input matrix, what if this is not, uh, what if its rank is not n? What if its rank is smaller than n? So if its rank is smaller than n, then what we can do in that case is we can compute uh, we can compute a subspace of Rn, which is orthogonal to the null space of A. When we construct the subspace orthogonal to the null space of A, what we can force uh, uh, yeah we can force y to be 0 uh, on the null space of A, and we can pick this V from the subspace which is orthogonal to the null space of A. And then so that would impose some additional constraints on the optimization program that can make the program slightly more complicated. So this is the simplest case. I'm just giving an example how to proceed in an example case like this. So we want to minimize this such that there exists some v for which this thing holds. So now, of course, this v is like an additional parameter into the problem, and so we when there are these kinds of additional parameters that go into the problem, they're added as follows. So we'll solve this in this way. We solve for minimization over v, minimization over these yi's, sum over of I yi minus ai times c of ei squared, uh, subject to the criterion. So this is an outer minimization program. So in this minimization program, the matrix y annihilates v. Okay. So I hope you understand this. There's a subtle difference between this and this. In this case, the v is actually fixed. Let me write it over here, such that, and put a such that. So in this inner optimization program, the v is fixed. For a fixed value of v, what I want a matrix which has the smallest difference in the Frobenius norm, and which also when multiplied with y gives 0. Uh, okay. Uh, so this kind of a problem. So v here is fixed. Okay. Assume here for now that v is fixed. The overall the global minimum is obtained by then varying v. We also vary v, and then we obtain the global minimum. Okay. So if we solve this inner optimization problem, the inner optimization is basically this. It is minimum of yi sum over of I yi minus ai squared c times ei such that uh, such that y, but what is y? Y is nothing but equal to yi ei, sum over of yi ei, such that sum over of yi ei on v is equal to 0. Right. So now, the way to solve this is basically using what we call as Lagrange multipliers. So this is an optimization problem subject to a constraint. So we introduce what we call as Lagrange multipliers. So the way to do this now is this: we minimize uh, over yi's and some additional parameter called lambda, sum over of I, uh, yi minus ai squared c times ei plus, yeah, uh, plus there is a sequence of linear relationships which need to be satisfied. Uh, so this can be expressed as a uh, uh, as something like this. So lambda is basically a vector over here. Uh, Lambda belongs to Rn. It's a vector, and we're going to write this as equal to lambda transpose uh, sigma yi ei times b. So this is the optimization problem that we need to solve. Okay, I hope it's clear how we are getting this. Uh, this comes from the theory of Lagrange multiplier. So let me just briefly also let me briefly write this. So uh, if we have an optimization function to solve, let's say we're solving for some optimization function x, where x is some vector Rn, and f is some map from Rn to R, and we are given some constraints. So a constraint would be something like this. We're given constraints of the form g1 x is equal to 0 up to, let's say, some gs x is equal to 0. Okay, so each of these gi's are maps from Rn to R. So when we are given fx such that these constraints have to be satisfied, then oftentimes we assume certain additional parameters and we solve for this. So fx, we don't assume. I mean, this is the method for solving it. There is a reason why this method works. This can be interpreted from some. This can be interpreted geometrically, but I'm not going into that. Uh, Assume that all these f, g, g1s and gs's, they're all like differentiable functions. They are they have at least up to two orders of derivatives. So then we solve for this optimization problem, lambda one g1 up to lambda n gn. So the minimization is is no long is also is over x and also over lambda one to lambda s. Okay, and then we go about doing it in the usual way. If we denote this thing as some function of x and the lambdas as well, then we proceed in the usual way. We compute all the partial derivatives, del f upon del x and del f upon del lambda j's, and we set them to equal to 0. And basically, that's how the minimum is going to be computed. So over here, if we have a constraint like this, recall V is fixed over here. So V is fixed, and we have a set of linear relationships. Uh, if we have YV is equal to 0, then of course we can write this y as uh, we can write this y as a collection of rows. So let me write y as y1, y2, and up to uh, yn. So these are the rows of y. Then yv equal to 0 is just is basically telling me that yj, inner product of yj with v is equal to 0. So that is y transpose. Sorry. So this is the yj transpose times v is equal to 0 for j from 1 to n. Now,
Shall I ask a
so
question?
these are the constraints that have to be set. Yeah, please.
Uh, Actually, this Lagrange multiplier is very well used in physics also, and
Yeah, yeah, yeah.
I could not understand this condition y v equal to 0. Where from it is coming, for what purpose it is used? That I
Ha, ha, ha.
don't.
Okay, okay, okay. So let me again go back. So what is our objective? Our objective, so we are given a matrix A, which is rank n. Assume A is a rank n matrix. And we want to compute a matrix A tilde such that the rank of A tilde is strictly smaller than the rank of A. Now, if the rank of A tilde is to be strictly smaller than the rank of A, that means there must exist some V, some vector V, such that yv is equal to 0. So y is basically my optimization variable. So the optimal value of y will be equal to A tilde. So what I want is that like it has to be 0 at some vector v. Only then can I say that the rank of A tilde is smaller than the rank of A. I hope this is clear
Okay,
why we
okay.
want. Okay,
Yes, yes.
so now what we want to solve this minimization program such that there exists some vector v. Okay, but you do not know what vector we are talking about. So to solve this problem, we are going to solve a two-step minimization program. In the first step minimization program, uh, we fix v. Okay, so let's say we have fixed v in this inner minimization program. We have fixed v, and we want to get a an approximation of a uh, such that uh, such that y times v is equal to 0. So y is my approximator, y v is equal to 0, where v is fixed. So here v is fixed uh, in this optimization program. Now, once that I get that approximation, so I'll get some kind of an approximation. I'll call that A tilde, but this A tilde depends on V. I get some A tilde V as a function of V. Now I want to minimize this also. I want to minimize. Uh, I want to minimize this as well. So therefore, we have this iterated minimization scheme. Okay. Uh, and uh, now what I'm doing is I'm trying to solve this inner minimization program. The inner minimization program, v is assumed to be fixed. So if v is assumed to be fixed, then yv is equal to 0 can be expressed as a set of linear conditions. Y v equal to 0 is basically equivalent to saying that the inner product of each of the rows of y multiplied with v is equal to 0. So we have a set of linear relations, and then the idea of Lagrange multipliers comes into play, and we can write this inner program as solving for this optimization program. And when we solve for this optimization program, I'm not explicitly computing all the derivatives and all that. Uh, what we get is as follows. Um, hmm. Okay. Yeah. We get this. We get as follows. We get uh, each yi is equal to uh, xi, not xi, sorry. Each yi is equal to ai minus uh, 1 by 2 c times ei uh, b transpose a transpose dv dv uh, pi. And what is dv? So dv is another matrix where dv is equal to uh, sum over of I goes to 1 to n 1 by 2 times c of ei ei of v times ei of v transpose. Yeah, sorry, one quick thing. Uh, yeah, sorry, this is not dv, this is dv inverse. Okay, so it's a pretty lengthy looking expression. Uh, so we are going to get each yi to be equal to this, right? And uh, so now we want to minimize. Uh, so now we want to minimize over v uh, yi minus ai times squared times c of ei. Now each yi, you can plug in this value and get an expression which you then minimize with respect to v. So you again differentiate now with respect to v this time. So you're varying v now, and and yeah, and uh, the yeah, and that's how we obtain the global minimum. So this is just one way of this is a particular special case. There's no need, in my opinion, to remember this result. Uh, uh, in a lot of actual problems that may be given to us, we should be able to find other ways of solving this. We do not necessarily have to solve such a large optimization. But this is just giving a flavor as to how these problems of low rank approximation can be changed into a problem of optimization in the following way, and then we can use analytic methods to solve them. That roughly brings us to the end of the theory discussion. Now let's look at some of the problems, and then it will become clear how to apply the theory. Okay, let's see. Okay, so in the first example, or in the first problem, uh, there we the question is what is the best rank approximation of A where the SVD of A, uh, where the SVD of A is not necessarily given, but the singular values of A are given. So as we discussed that if we want to compute the best rank approximation of A, then the best rank approximation would be this AK tilde is going to be equal to sigma 1 U1 V1 transpose up to sigma k UK UK VK transpose. Right. So now this is going to be the optimizer. So what is AK A minus AK tilde? Okay. So then A minus AK tilde is equal to sigma k plus 1 UK plus 1 times VK plus 1 transpose up to the rest of the remaining terms. So just to give uh, like a small result, if you have any matrix B which is expressed in this way, uh, let's say B is expressed as some lambda uh, one U1 V1 transpose up to let's say some lambda M UM VM transpose, where UIs and VIs are orthogonal. Where these UIs and VIs are basically they are they're orthonormal vectors basically. Uh, so then the Frobenius norm of B is basically going to be equal to let me write it. Frobenius norm of B squared is equal to lambda 1 squared up to lambda m squared. And this can be seen easily. So recall that the Frobenius norm of B is equal to trace of B transpose B. This is the square of the Frobenius norm. So trace of B transpose B. Uh, so if you just uh, take the transpose, uh, well, that is equal to lambda 1 V1 times uh, U1 transpose up to lambda M VM transpose acting on yeah acting on lambda 1 U1 V1 transpose plus lambda M UM VM transpose. So well, this is equal to so as I said, the vectors U1 to UM. So this is like an SVD. So the vectors U1 to UM are orthonormal to each other, and so they are like an orthonormal set. And the vectors V1 to VM are also an orthonormal set. And so what we get is this: we get lambda 1 squared. Uh, so we get trace of lambda 1 squared uh, V1 transpose plus lambda M VM transpose. So of course now trace distributes. So this is equal to sum over of the trace of lambda I squared VI transpose, right? And you can easily check that this uh, VI VI transpose. Well, this is just equal to uh, the 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 two norm of it. So this is sum over of lambda I squared times the two norm of Vi, and this is just equal to 1. So this is equal to sum over of lambda I. Okay. So the trace of a matrix, so the Frobenius norm for matrix becomes equal to this. And so if the low rank approximation is this, then A minus I tilde K is the remaining terms. And we know, and from there we can get the correct answer for this. Okay. The correct
Okay.
answer comes from this.
Okay.
All
Okay.
right. Let's look at uh, hmm. Problem number 2 is also similar to problem number 1 in the sense that the idea has been discussed, so this should be straightforward to solve. Right. Uh, yeah, in this case, instead of using the Frobenius norm, the 2 norm is being used. And we know that if a matrix uh, is this, so basically the SVD of A minus A tilde K is equal to this. The largest singular value of this is equal to sigma K plus 1. And well, the correct answer is is obvious. The only difference is they're using 2 norms. So we know that for 2 norms, uh, the the 2 norm is going to be equal to the largest singular value. Uh, so we can easily deduce the largest singular value from an expression like this. Okay. Um, let's look at the third problem. Yeah, the third problem is that we given A and we want to find the nearest rank one approximation of A in the Frobenius norm. Again, this is just a straightforward application of all that we have been discussing thus far. A is given, the SVD of A is given. Need to find the nearest rank one approximation of A. Again, should be fairly a easy problem, just a computational problem. Okay. The fourth problem is also uh, the fourth problem is also similar. There they want us to compute. Let me just copy the fourth problem also. Here, so here instead of the I mean here instead of rank one approximation, they want us to compute a rank two approximation. Again, the SVD is given to us. We know how to compute the rank two approximation. Again, this is simple.
Shall
The
I
only
ask?
difference is that
Shall I ask
yeah,
a question?
yeah,
Rank
yeah,
K
please, please.
approximation means up to K we have to take. Is it?
Yeah, rank K means you take the first K. Uh,
Okay. Yes.
you take the first K. Here, rank 2 means you take up to these two. That's it.
Right.
Yeah.
Okay. Okay.
This
Understood.
this is for both the Frobenius uh, uh, and the L2 norm. This is that theorem, that Eckhart Minsky theorem that we were discussing. Okay. Yeah, I mean there are a bunch of problems uh, which are similar. Question 5 is also similar to that. Uh, let's look at questions 6 and 7. They are an application of the constraint optimization that we were talking about. So let's come to question 6. Question 6 is this. So we're given a matrix A, and we want to find out a rank 2 matrix such that the zeros are not perturbed. In other words, uh, uh, we want to compute a matrix A tilde such that A tilde looks like this. There are terms here, 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 but these are zero. Okay. Uh, right. So the terms here are equal to 0. So of course, I mean, this fits into the template that we were discussing before. Uh, the space of all matrices uh, uh, where these and these are equal to 0. This itself is a linear subspace of the space of all 3 cross 3 matrices, and we can use the strategy that we discussed before. But we should not go along that path because there is probably an easier way to solve it. Okay. Uh, Instead of going along that formula there should be an easier way to solve it. So the easier way to solving it comes from an observation onto the shape of the matrix A. So notice that the matrix A, or in general the subspace of matrices that we are dealing with, are block diagonal matrices. So let me write it. So they are block diagonal matrices, and so there is a 2 cross 2 block here, and then there's a 1 cross 1 block here, right? So this when we have block diagonal matrices, then the rank of a block diagonal is the sum of the ranks of the blocks of that matrix. Okay, let me just write it. This is obvious that the rank of a block uh, diagonal matrix is equal to the sum of ranks of its blocks, right? So we want to compute a rank 2 matrix. So there are two ways in which this can be uh, a rank 2 matrix. So the first is that the rank is concentrated in this block and this term is equal to 0, or or this term is non-zero and the rank of this block is equal to 1. So there are two possibilities, right? Uh, so now let us solve the problem. So there are two cases to look for. In the first case, in the case one, we're looking at a block. We're looking at matrices of this kind where the rank 2 is over here and the term over here is equal to 0. Okay, so this is case one. So in case one, uh, we have an upper block which is of rank 2. Okay, uh, upper block of rank 2. Okay, so let's write this upper block. Uh, let's just write uh, for the sake of uh, simplicity. Let's write this as equal to y1, and let's write this as equal to y2. So y1, let us write y1 equal to y1, y2, y3, and y4. It is given to us that y1 is uh, y1 is of rank 2, because in the first case we are assuming that the rank of y1 is equal to 2 and the rank of y2 is equal to 0, which is just equivalent to saying that y2 is itself 0. So the rank of y1 equal to 2 basically is equivalent to saying that the determinant of y1 is not equal to 0. Okay. So what is determinant of y1? Determinant of y1 is equal to y1, y4 minus y2, y3. Okay. So in the first case, we want to solve for uh, this. This is not equal to 0. So in the first case, we want to solve for um, y1 minus 1 squared plus uh, y2 minus 1 squared plus y3 minus 1 squared plus y4 plus 1 squared. This is the minimization such that sorry, such that y1 y4 minus y2 y3 is not equal to 0. So this can be uh, um, hmm, right. So this condition uh, is also uh, yeah. So this condition is also included into this optimization program. Uh, right. How to include this? Just give me 1 minute. Need to look up one thing. Just give me 1 second.
From the choices, we can see that the lower block is not zero.
Yeah, but that would be like option matching. I want to give like a I want to give
Theory.
like
Okay.
a general like a more general step-by-step way of solving a problem like this. So yeah, so in order to solve for this, uh, right? Uh, okay. So if you set hmm, yeah. So yeah, I mean this is we can easily see what is going to be the minimizer. The minimizer is just going to be equal to y1 equals to 1, y2 is equal to 1, y3 is equal to 1, and y4 is equal to minus 1. So essentially, in case 1, we set y1 to be equal to the upper block of this, right? Uh, and when you set y1 to be equal to the upper block of this, then the difference that we get is equal to 3. Okay. Uh, in the second case, in case 2, uh, in case 2, we have as follows. we have y. Again, y is this block, y1, and then y2. So in this case, rank of y1 is going to be equal to 1, and y2 is not going to be equal to 0. Okay. So again, writing y1 as equal to y1, y2, y3, y4. But this time, well, this time rank of y1 is equal to 1. And so what this means is that one of the rows can be represented as a linear combination of the other rows. So we're going to write this y as y1, uh, as y1, y2, then uh, alpha times y1 and alpha times y2, where alpha is some real number. Okay, and yeah, and yeah, okay. So if so, this is y1. So now again, let's solve for this optimization problem. We have uh, y1 minus uh, y1 minus 1 squared plus uh, alpha y1 minus 1 squared plus y2 minus 1 squared plus alpha y2 plus 1 squared. Okay. And of course, the quantity over here would be set to 3 because we want to minimize the Frobenius norm. So uh, this is just going to be equal to 3. And we want to minimize this quantity. This is to be minimized over y1, y2, and alpha. Um, so yeah, I mean, this is a simple optimization program to solve. Uh, Once you solve for this optimization program, you get a y1, y2, and an alpha, and you set that to be equal to y1. Uh, so I'm not solving for this. I'm leaving this to be solved. Hmm. Yeah, so I'm leaving this to be solved. So in general, so this is an example where uh, even though we are not necessarily using the same template that we discussed before, where we have these very lengthy expressions and we're not necessarily doing it this way. We are exploiting some easily we're exploiting some structural properties of the matrices. So in this case, the structural property that we exploited was the fact that we are looking at block diagonal matrices. So for block diagonal matrices, we have an easy understanding of where the rank of that matrix is concentrated. Like in particular, we need to look at only only the blocks of the matrix uh, to decide where the rank is going to be concentrated. And based on that, we have a much simpler way of expressing this optimization problem. So it's good to keep in mind that where possible, we should look to exploit some structural property that uh, the matrices can have. In this case, block diagonal being one of. Okay, hope this is clear. Uh, Now we can look at uh, Let's look at some of the remaining problems. Again, mostly they have been covered by uh, today's discussion. Um, okay, I think the rest of the problems should be doable. Uh, if you have any questions, you can ask me. Otherwise, we'll uh, we'll we'll end it here.
Actually, computational complexity
Okay.
is not discussed in the class. In the
Oh,
case of
okay.
SVD,
Okay. Okay. Right. Hmm. Okay. So the computational complexity of the low rank approximation scheme is the same as the computational complexity of computing the SVD, right? Uh, yeah, it is effectively the same as computing the SVD. So now that depends upon the choice of the algorithm. Um, that's well,
maybe the complexities were discussed in earlier classes. Maybe I have to go through that and find.
in general. In general, the computation, well, let me just write it. The complexity of SVD, in general, SVDs can be computed in OM n squared time. We have an m cross n matrix. There exist algorithms that will compute the SVD in OMN squared time. Okay. So whatever the complexity of computing SVD is, this is the same complexity is required to compute the rank approximation. So that is the answer.
Okay, can you comment on the previous ninth question?
Ninth question. Oh, okay. Yeah, I mean, if I, I'll most likely end up spelling out the answer then. But so for this ninth question, so okay, so let us examine the options. When would uh, when would low rank approximation be useful, right? Uh, um, so low rank approximation would be useful when if you have an image. So what is uh, yeah? So we can think of the image as uh, as being uh, as by this large matrix, right? We can have like a large matrix representation of the images, and so low rank. low rank approximation is going to be useful when okay, I mean, let's not talk about images. Let's say you have any matrix, okay, or any operator, okay. If you have any operator, then uh, we can there's something called the rank of the operator. The rank of the operator is going to be the rank of the image under that operator. Now, what if uh, uh, wait, let me think about this a little bit. What is the best way to explain this? Um, hmm, hmm. Okay. Let's try to answer it this way. Let's say you have a set of vectors. Okay. Uh, if let's say you have n vectors, or let's say you have 1,000 vectors, but uh, all those thousand vectors lie on a uh, on a plane of dimension 10. Let's say if all those 1,000 vectors lie on a plane of dimension 10, then well, there's no need to do any image compression. There's no need to do any matrix compression. Uh, you can just say that well, you can just say that uh, all the vectors are lying on a plane of dimension 10, and so it's already a sufficiently low rank. Okay, but now uh, suppose that all the vectors do not lie on a plane of rank 10, or do not lie on a plane of dimension 10, but they lie very close to a plane of dimension 10. In other words, if you take the vector, in other words, I can find a plane. Let's say I'm just giving out like a hypothetical scenario. Let's say I can find a plane such that if I do the orthogonal projection of each of the vectors on that plane, then the orthogonal complements would be very small. Okay. So let me draw a picture. A picture would be like this. Uh, let's say you have a lot of data points like this. Oh no, let's not take this example. Let's take this example. Let's say let's say this is in 2D, and you have a lot of data points like this. So if you look at the image of the data points, then uh, then it appears that they have a 2D shape to it. Okay, but if you draw a plane like this, if you draw a plane like this, you can say that that all the data points are extremely close to this plane. Okay, and so if you project these data points onto this plane, well, all the data points are now going to lie on uh, on uh, uh, on the plane. So let's say if this data set, yeah, I mean, let's say if this data set, which is let's say this data set has 1,000 points and equals to some 1,000 points are there. Okay, uh, let's say you arrange them in the form of matrix. So uh, you have a 2 cross n matrix. Uh, this is a 2 cross Pn matrix, and each point you represent it as a column. So P1 up to some Pn. Okay. So now let's say you have a plane, let's call it H, and you have a projection map onto that plane H. So let's denote that projection map by some function, let's call it pi, and you have projected each of these P1s to Pns onto H. So if we call this matrix as A, let us construct another matrix AH, where AH is equal to this projection map pi H on P1 up to pi H on Pn, right? This is a 2 cross n matrix. So, so the rank of this matrix was a rank 2 matrix, but the rank of this matrix is a rank 1 matrix, right? But uh, but all the points, but all the so you were able to do this effectively because you could find a plane H where all the points lie very close to this point H. And so if you take the Frobenius norm of A minus AH, Frobenius norm squared, well, the Frobenius norm is equal to P1 minus pi H of P1 squared. So this is the norm of this vector squared plus up to Pn minus pi H of Pn norm squared. Now, if now because these points lie very close to this plane H, each of these terms are going to be very small, and so the rank one approximation of this rank 2 matrix makes sense because you have this property. Now, now think of a different case where uh, where you have something like this, where the data points are situated like this. They are very much symmetric. Okay, so if the data points have a lot of symmetry between them, right? Uh, so then what happens is that you cannot construct a plane like this. Okay, so so now let's go back to the question. Let me copy this question. Now this becomes like a question in statistics. So uh, if we are to uh, translate the notions that we discussed here to the options that are given, like what 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 can possibly be true? So the first option is images have a high degree of randomness. Okay, so if there's a high degree of randomness, if I ask you, if I give you, let's say, two images, if I give you, let's say, two sets of points, so this is one set of points, and this is another set of points. And if I ask you which set of points have a higher degree of randomness in them, okay, the answer is the second set of points have a higher degree of randomness in them. The so-called entropy in the second data set is higher than the entropy in the first data set. Okay, so so if the randomness is higher in the system, the rank is also going to be higher. Okay, it does not make sense to perform a low rank approximation for a system which is highly random. Okay, a low rank approximation will never accurately capture a highly random data set. Okay, it can a low rank approximation can only capture a data set which is well behaved, which there isn't a lot of randomness. Now you have to use this idea to solve the problem.
Okay.
So out of options A, B, C, D, there is one option which basically suggests this idea.
Okay, I will go through that.
Yeah. Okay. Okay. So that brings us to the end. This is the last. Uh, this is the last week for the course. Uh, I hope. I hope this was a useful course. Uh, this was definitely a learning experience for me. I'm by no means an expert in matrix analysis, optimization problems on matrices, and so on. I do not have a background in that. So I got to learn quite a few things from this course. Hopefully, you also learned like the course. Uh, so yeah, thank you so much for being a part of this course. Uh, yeah. Uh, until next time. Goodbye.
We also thank you, sir, for helping us to solve the problems. Thank you very much.
Yeah, sure. It was a learning experience for me, and thank you for all the questions, for all the participation. Yeah, thanks a lot. Yeah. Until next
Okay.
time. Goodbye.
Bye. Bye. Bye.
Bye.